So now we're going to talk about energy. That's what chapter 10 is all about. So here in this chapter, we're going to look at the relationship between chemical reactions and energy. And what you're going to see is that in some cases, you have chemical reactions where energy is lost. In other reactions, you have situations where energy is gained. But first, of course, we have to define what we mean by the term energy. And energy, by definition, is simply the capacity to do work. Now, whenever we're talking about work, we're talking about the ability to move an object a certain distance. That's basically what work is, right? So any object or anything that has a capacity to do that is said to have energy. And these are the main types of energies, but we can simply put these main types of energies into two broad categories. You have potential energy, which is the energy an object has by virtue of its relative position, and of course that means relative to some other object. And then, in the case of the example being shown here on the screen, we're talking about the energy of a ball relative to the earth. So if you lift the ball up to about 20 feet, then it will have a certain amount of potential energy relative to the earth. And then if you lift it further to 50 feet, its potential energy relative to the earth will increase, and so on. All right? So that's one example. So potential energy can also be seen as stored energy. Gasoline, for example, is another source of chemical potential energy. And this energy is released when gasoline is burnt. Gasoline actually is made up of a different compounds, hydrocarbons, organic compounds, which have energy locked into their bonds. And when you burn it, it releases energy in the form of chemical potential energy, usually that's manifested in heat energy and light. And then the result would be products which are formed. And the thing about these products is that their energy would be less compared to the gasoline and the oxygen which reacts with the gasoline when combustion takes place. All right? The next type of energy, next category of energy is known as kinetic energy. And it is the energy an object has by virtue of its motion. So anything that is moving has kinetic energy. So these are just some examples of kinetic energy. If you have a flag waving in the wind, or a bouncing ball, or a running man, or somebody just simply running, or a soccer player who is also running as well, those are examples of kinetic energy. All right, so let's talk about heat, which is a form of kinetic energy. In fact, heat is the form of energy which is associated with the movement or the motion of small particles of matter. Now, people tend to confuse the term heat and temperature. Temperature is something different. Temperature is a measure of the intensity of heat, or basically how hot or cold a system is. All right? The units of heat energy, there are a couple of units. You have the SI unit of heat, which is known as the joule unit. The joule unit is another, it's actually a result of the combination of several units. Let me just write a little thing here. Joule unit is the same thing as kilogram meter squared over second squared. All right? So that combination of units is the same thing as a joule unit. Another unit, which is an older unit, a non-metric unit, is the calorie unit. All right? And there's a relationship between the two. 1 calorie is equal to 4.184 joules, and that is by definition. That is an exact relationship. All right? Okay, and by definition, this is the amount of heat that will raise the temperature of 1 gram of water by 1 degree Celsius. And we're going to say more about this when we get to a discussion of specific heat. Okay, so just to illustrate the difference between heat and temperature, remember now, heat is the form of energy that's associated with the motion of small particles of matter, while temperature is basically a measure of how hot or cold a system is. So to illustrate the difference between these two, let's say you have 100 grams of water at 20 degrees Celsius in one container, and 200 grams of water at 20 degrees Celsius in another container. All right? And so therefore these two are at the same temperature. And then we start heating them, right? What you'll find is that in order to raise the temperature for each of them from 20 to 30 degrees, more heat is needed in the case of the 200 grams of water. All right? So this illustrates the fact that heat and temperature are not the same thing. All right? More heat is needed simply because you have more water here, right? You have double the amount of water here in container B compared to container A, and therefore you need double the amount of heat to raise the temperature of water to the same extent. All right? So I hope that helps to, distinguish between the two terms heat and temperature. All right? Okay, so let me talk about specific heat. All right? The definition of specific heat is shown here. It is the amount of heat needed to change the temperature of 1 gram of a substance by 1 degree Celsius. In other textbooks, you might see 1 Kelvin here replacing 1 degree Celsius. Doesn't make a difference. The actual numerical value of the specific heat will still be the same. I'm going to say more about that later on. So what you'll find is that the specific heat is a physical constant associated with different substances, and it's pretty much a physical constant just like other physical constants like density, like melting points, like boiling points, and so on. In other words, we can use the specific heat as one of those things to help to identify a substance. So as you can see here, different substances have their own values of specific heat. Of these substances, water has the greatest, and that is primarily due to a phenomenon known as hydrogen bonding, which we should get into much later on in this course. So water has a specific heat, as I said before, 4.184. Ethyl alcohol, or ethanol, same thing, has a specific heat of 2.138. And then what you'll find is that metals typically have relatively low specific heat. So as you can see here, aluminum, iron, and so on, their values are less than 1 when the units is joules per gram degree Celsius. All right? So here we have the units of specific heat in joules per gram degree Celsius, and here we have the units of specific heat in calories per gram degree Celsius. All right? Okay, so as I said before, this would be the units of specific heat if we have heat expressed in joules, right? But we can also express specific heat in terms of calories per gram degree Celsius. All right? And we can actually establish an equation, a relationship between these terms, the mass, the specific heat, the change in temperature, and the heat lost or gained. And this is the equation right here. Q is equal to mass times the specific heat, represented by lowercase c, times the change in temperature, right? And of course, based on the units used for Q, M, and delta T, you can figure out what the units of C is, all right? So that's a relationship that ties these 3 or 4 terms together. So let's look at some examples using this equation. This question is asking for you to calculate the specific heat of a solid in these units, joules per gram degree Celsius and calories per gram degree Celsius, if 1,638 joules raise a temperature of 125 grams of the solid from 25 degrees to 52.6 degrees Celsius. So the equation you're going to use, go to the pen function. So the equation you're going to use, of course, is Q is equal to M times C times delta T. So therefore, C, which is what the question is asking for, would be equal to Q over mass times delta T. So all you have to do is plug the numbers in. For Q, it is 1638 joules divided by M, which is 125 grams, times delta T, which is the difference between 52.6 degrees Celsius and 25.0 degrees Celsius. All right? So typically when you get a problem like this or a setup like this, you work out what's within the parentheses, 52.6 minus 25, and I end up with 27.6 degrees Celsius. Whoops. 0.6 degrees Celsius. And then I just do the calculations, the rest of the calculations. So 1638 divided by open parentheses 125 times 27.6. And the answer I get here is 0. Hold on 1 minute. 0.474, and the units would be joules divided by grams degrees Celsius. And that's how you do that. All right, so that's pretty straightforward. You just rearrange the equation to get what the question is asking for, which is a specific heat, and then you just simply plug the numbers in for Q, M, and the two temperatures to find delta T, and you get your result. Okay, let's talk about the law of conservation of energy. Basically, what this law says is that energy can neither be created nor destroyed, but it can be transformed from one form of energy to another. All right. So, for example, we can apply that principle along with what we learned about specific heat to this particular example here. Okay, so this question says a sample of metal with a mass of 212 grams is heated to 125 degrees Celsius, and then it is dropped into 375 grams of water at 24.0 degrees Celsius. If the final temperature of the water is 34.2 degrees Celsius, what is the specific heat of the metal? So let's think about what's happening here. We have metal. We have a metal which is heated to a very high temperature, 125 degrees Celsius. And we place it in water, which is at a lower temperature, which is 24.0 degrees Celsius. So what's going to happen is that you're going to have a heat transfer from the hotter metal to the cooler water, right? So the amount of heat that is lost by the metal will be equal to the amount of heat which is gained by the water. And that heat transfer will take place until the temperature of the metal and the temperature of the water will be the same, all right? So that's basically what you'll be using in order to solve this problem. So the first thing I'm going to write down here is that the Q, I'm going to use QW to represent the amount of heat that is lost, that is gained by the water, and QM represent the amount of heat that is gained, QM represent the amount of heat that is lost by the metal. So water will be gaining heat, the metal will be losing heat, all right? So QW is equal to QM. And then what I'm going to do is write down expressions for QW and QM. So for QW, it is the mass of the water times the specific heat of the water times the change in temperature of the water. And that would be equal to the mass of the metal times the specific heat of the metal times the change in temperature of the metal. Now remember, the question is asking for the specific heat of the metal. So therefore, I would rearrange this to get the specific heat of the metal is equal to the mass of the water times the specific heat of the water times the change in temperature of the water divided by the mass of the metal times the specific heat of the metal. And then what I would do is now put the numbers in. Now, the mass of the water is given. It is 375 grams, right? The specific heat of water, that would have to be given to you. That would be equal to 4.18 joules per gram degrees Celsius. And now we get to the change in temperature of the water. And here you have to be careful. The change in temperature of the water would be the final temperature of the water, which is 34.2 degrees Celsius, minus the initial temperature of the water, which is given as 24.0 degrees Celsius. And we divide that by the mass of the metal, which is given as 212 grams, times the, this should be delta Tm here. Let me change that. Delta Tm. The change in temperature of the metal. Now, the change in temperature of the metal would be the 125 degrees Celsius, 125.0 degrees Celsius, minus the final temperature of the metal, which will be the final temperature of the water, which will be 34.2 degrees Celsius. All right? And that's it. All we have to do is use our calculator. Of course, we have to work out what's within the parentheses first, so let me do that now. 34.2 minus 24.0. So that part is equal to 10.2 degrees Celsius here. And then down here we have 125 minus 34.2. And that part is equal to 90.8 down here. 90.8 degrees Celsius. And then we just have to do our number crunching for the rest of it. 375 times 4.18 times 10.2 divided by 212 divided by 90.8. And according to my calculation, this works out to be 0.831. 0.831 joules per gram degrees Celsius. All right, and that's basically how you would do that. All right, so this is the application of the conservation of energy law to a problem which also involves specific heat. Okay, we're going to stop here, and we're going to continue our discussion about energy changes when it comes to chemical reactions. All right, until next time.